Hello everyone, welcome to webinar on high-rise building design with construction stage analysis using MIDAS Gen program, a one-stop solution for building and general structures. When it comes to high-rise buildings, MIDAS Gen has these special features. Under seismic specific functionality, there is static seismic loads, response spectrum analysis, time history analysis, linear as well as non-linear, with base isolators and dampers. Then pushover analysis can be performed, fiber analysis and capacity design can be done in MIDAS Gen as per Eurocode 8. MIDAS Gen has comprehensive design in RC design, steel, SRC, there is footing design as well as slab and wall design as per Eurocodes. Another major high-rise specific functionality, there is 3D column shortening that reflects the changes in the modulus of elasticity, creep and shrinkage. For that, construction stage analysis is important. It can also account for the change in geometry, supports and loadings. In MIDAS, there is a very useful function that is building model generation wizard. It can also incorporate automatic mass conversion. Material stiffness changes for cracked section analysis can also be included. With all these functionalities, it is very important for the program to be very user-friendly. So there is intuitive user interface of MIDAS Gen that includes works tree, which can input summary with powerful modeling capabilities. Modeling is easily created in MIDAS Gen. We can define flow loads by specifying area on inclined planes as well. There is built-in section property calculator, and there is a great interface between Tekla and Revit and STAAD as well. Next, let us discuss regarding construction stage analysis. Generally, structures are analyzed assuming that the structure is built and loaded in a moment. Actually, it is the live loads, wind loads and earthquake loads applied to a complete structure. However, the dead load is a type of sequential loading. Since most buildings are constructed as one story or several units at a time, we need to consider the construction sequence. I would like to take an example of a simple frame here. Let us compare case 1, which is the conventional analysis, and case 2, which is construction stage analysis with two stages. In one stage, support and first level is constructed, and in the second stage, the next level is constructed. As a result, we see how significantly the moments vary between the two cases. The moment at the support is 8.4 kN in case 1, whereas in case 2 it is 17.1 kN. Thus, with the shortening of structure, moments increase ultimately. These moments, if in limit, can be compensated with more reinforcement. This is usually considered in short structures. But for high-rise structures, the moments would go higher and thus a necessity of performing column shortening analysis arises. The compensations are then in the form of increasing the heights of vertical elements. So CS analysis is also required for long span trusses. As we see here, the boundary support changes while erecting and placing the truss in position. Also used in bridges and in buildings for long span slabs, and differential column shortening in high-rise buildings as explained earlier. So in short, where there is change in support conditions, loading and varying material properties, construction stage analysis is required to be performed. That brings us to the next topic of discussion, that is column shortening and related issues. When any member is loaded with axial loads, it undergoes axial deformation, that is PL upon AE, following linear elastic strain equation. Now, why is this important? Shortening won't be same for all vertical members due to several reasons. Column P1 will have deflection delta L1, column P2 will have deflection delta L2. This differential shortening in vertical members may cause additional forces and stresses in beams and slabs. Column shortening effect becomes more significant with increase in height of structure. We hence need special consideration in design and construction. As an example, column shortening analysis of an 80-story building, steel building as well as concrete building was done. As a result, the steel structure had elastic shortening of 180 to 255 mm, whereas concrete elastic shortening was 65 mm. Even though 65 mm, the total shortening of the concrete structure was 180 to 230 mm. This means that the inelastic shortening of the concrete structure was more significant. It was almost 1 to 3 times the elastic shortening. Hence, the inelastic properties varying with time shall be considered for high-rise structures. The inelastic properties include creep and shrinkage and modulus of elasticity that varies with time. So there are two prerequisites for accurately and efficiently predicting these effects. One is the reliable data for creep and shrinkage characteristics for particular concrete mix, and second is a reliable analytical procedure for the inclusion of these time effects in the design of structure. In MIDAS Gen, some of the popular predicting methods for predicting creep and shrinkage are ACI 209, Bazin-Baweja P3, CBFIP, the PCA method, which uses Mark and Fintel, Eskagosian Hal Iyengar method. Then there is GL 2000, Gardner and Lockman, that is. And as well as we have the Eurocode. Now, as per Eurocode, the total strain at any time t may be expressed as the sum of the instantaneous creep and shrinkage components. The instantaneous strain in concrete at any time t is expressed by this formula, that is stress at time t on elastic modulus of concrete at time t, which is further given by this particular equation. Creep is the time-dependent increment of strain under sustained stress. As per Eurocode 2, the creep deformation of concrete is predicted with this formula. In case of shrinkage, the total shrinkage strain is composed of two components, the drying shrinkage and the autogeneous shrinkage strain. The drying shrinkage strain is due to the moisture loss in concrete, and the autogeneous shrinkage strain is caused by hydration of cement. Here, the notional size of elements come into picture. In short, the factors affecting creep and shrinkage in case of material is the concrete composition, that includes cement paste content, water cement ratio, mixture proportions, aggregate characteristics, degrees of compaction, then length of initial curing, curing temperature, curing humidity. Then when it comes to member geometry and environmental factors, we have under environment concrete temperature, concrete water content. Then the geometry factors are size and shape. Then the loading factors affect the creep only. So the loading history and the stress conditions, that is concrete age at load application, duration of loading period, the duration of unloading period, number of load cycles, types of stresses and distributions across the section, and stress or upon strength ratio are the factors. Looking at the issues due to column shortening, we see that non-structural as well as structural effects occur. The non-structural effects include the deformations in pipes, elevator rails, claddings, even cracks in partitions. Under structural effects, there is distortion of slabs or beams due to differential movements, and because of the indifferential shortening, there is gravity load redistribution that occurs. Overall, there are two shortening results. One is pre-slab installation shortening, which is shortening that takes place up to the time of slab installation, and the other is the post-slab installation shortening, which is the shortening of supports that take place after the time of slab installation. In case of RC structures, the pre-slab installation shortenings has no importance at all. This is because the compensation is done already by leveling the formwork of the slabs. After the slab has been cast and the loadings are coming onto the slabs, that is the post-slab installation shortening, due to subsequent loads and the creep and shrinkage come into picture for the reinforced concrete structure. Thus, the post-slab installation shortening is used for the compensation to get to the design level. In case of steel structures, the columns are fabricated to exact length. Also, the attachments to support the slabs are finalized. So, the pre-slab installation shortenings are hence required to be known. The compensation, in short, the total compensation will be the pre-slab installation shortening as well as the post-slab installation shortening. In practice, the procedure for column shortening is, firstly, initial column shortening analysis with code-based material and section properties, loads, and construction sequence is performed. The analysis results of load redistribution are observed. Then, with any modifications, the material properties are updated by material experiments of compressive strength, modulus of elasticity, creep, and shrinkage. Column shortening is then rerun. Here, the shortening of further stages are predicted and compared with shortenings on site. Then the model is updated by providing an amount of compensation which is then applied on the field. Let us look into the project applications of MIDAS Gen that have used column shortening analysis. The Burj Khalifa of 705 meters height, 160 number of floors, located in Dubai was analyzed in MIDAS Gen by the general contractor Samsung Development. In order to account for time-dependent concrete effect, a comprehensive construction sequence considering the creep and shrinkage effects was used to consider the time-dependent behavior. Another application is the SKS Chano in South Korea. It has 36 numbers of floors all having different shape. It is a composite structure having reinforced concrete core, some steel installations, and reinforced concrete composite frames. So let us see that in MIDAS Gen. Here we have SKS Treno model in MIDAS Gen program. Now let me show you the construction sequence used in MIDAS Gen for this structure. I'll start with construction stage 1. In the construction stage 1, we see that the core walls have been firstly constructed. This is the normal bottom-up construction stage. But the peculiarity of this structure is the top-down method used for the construction sequence. There are many competitive softwares that cannot simulate the top-down construction stage method. They can only simulate the normal bottom-up construction stages. But the part is that when we simulate the top-down construction stage, the boundary condition has to be changed at each construction stage. We can see that over here with the support conditions. These vary with the construction stages. So I'll just display this. So as you can see, the supports are varying for every location until it goes at the bottom. And then further we have got the normal bottom-up construction stages. But over here as well, we have got SRC sections. Now these SRC sections are also dependent on the construction sequence. Like firstly, the steel sections will be constructed, steel sections will be erected basically at the locations, and then further the column concrete will be casted. So we can see now as we go ahead with the construction stages, the concrete is also going to get cast. There are some other elements also that we're casting along with the same time. So such kind of a construction sequence can be modeled in MIDAS Gen. So I'll go back to the presentation now. Another one is the King Nam Hanoi Landmark Tower in Vietnam. These are twin towers of 49 floors each and one tower of 70 floors. It was a complete reinforced concrete structure analyzed in MIDAS Gen. So we have seen the general concept of column shortening analysis and the project applications in MIDAS Gen. Now for the live demonstration, I would like to discuss on the MIDAS Gen procedure for column shortening analysis. This is the flow chart in MIDAS Gen. Firstly, we create the model and define the materials and sections. Then, while assigning the boundaries and loads on the structure, we define element, boundary and load groups. We need to define the time-dependent materials like creep, shrinkage and compressive strength. The good part is these can be defined by users manually, which is required when experimental material properties are required to be defined. So let us go back to the procedure. After time-dependent properties definition, we define the construction stage analysis data. That is, the duration of stages and activation or deactivation of element, boundary and load groups in every stage. So I'll go to that page. This is the dialog box where the duration can be specified for each construction stage, and here the elements and boundaries and load groups can be activated or deactivated. The good part is the load step function. This allows the user to activate loads at different time intervals in the same construction stage. The program also provides with a tabulated construction sequence for easy identifications. In MIDAS, for construction stage analysis, there are three main stages for the model display. The base stage, in which model can be edited. The construction stage, in which the stages are activated. Here only elements, boundaries, and loads applied in that construction stage will be displayed. And lastly, this is the post-construction stage that appears after the construction stage analysis has been performed. Here the results from stage analysis are used and further analysis results using the transient loads other than stage loads like wind and seismic loads are displayed. So I'll go back to the procedure. So after we are done with the definition of stages, analysis is performed. The results for each stages can be checked. Let's see the results. For every stage, we can get all the results like deformations, reactions, moment diagrams, and everything. Absolute minimum or maximum results of envelope can also be checked among entire construction stages. And results of creep and shrinkage effects are also provided. After checking all these results, the program also provides with the column shortening results in the form of graphs. All you need to do is provide location of the vertical member and select which results are required to be extracted, like the post-slab results called as subsequent to casting and pre-slab shortening called as up to casting. This is the structural plan of the demonstration building. So now I'll go to MIDAS Gen program. So this is the building model that I have taken for the demonstration. This is the plan view. Now over here, this is the workstream menu in MIDAS Gen. So here the advantage is that with one glance we can see what all things we have incorporated, how the loadings and the boundary supports have been applied onto the structure. We can see here the material properties and the section properties defined, like the columns, the walls, the girders have been all applied with a separate material property. The thickness of the wall is 300 mm. The boundaries have been applied, fixed boundaries have been applied. There are some beam end releases also, and under the static loads, sulfate has been applied. Then floor finishes has been applied using the assign floor loads command, as well as the live loads have been applied onto the structure. So now we can go ahead with the properties definition, that is the time dependent properties definition. For construction stage analysis, we are going to have the creep, shrinkage and compressive strength time dependent property assigned to the linear material properties that we have already defined. The good part is MIDAS Gen has got user defined capability to manually input the experimental material property time dependent property results. So now we are going to go ahead with defining the creep and shrinkage. Here I'll provide a name as column, and we can choose the code, any code available over here for predicting the creep and shrinkage properties. There is CBFIP, ACI, PCA, combined ACI and PCA, Indian method as well as European is also available, and other methods are also there. So now I will be selecting the European method and then the parameters for calculating the creep and shrinkage properties, like the characteristic compressive cylindrical strength of concrete at the age of 28 days. So this was chosen, the linear material property was chosen as C3037. So according to the unit system, I'll be applying over here the characteristic compressive strength, relative humidity of ambient environment as 70%, and the notional size of member. Now the notional size of member would be separate for each and every column with different section properties. This is because the notional size of member is dependent on the sectional area and the perimeter in contact with the atmosphere. But no need to worry. In MIDAS Gen, this notional size of member is automatic. It can be calculated automatically by using these change properties. So here all I have to do is provide an arbitrary value of 1 meter and then go ahead with the next parameter definitions, like the type of cement, which is class N, and the type of code to be selected for concrete bridges or for general structure. Well, this would be a general structure, so I've chosen this one. And then the age of concrete at the beginning of shrinkage is 3 days. Then I'll click on this show result. Over here we can see the graph of creep coefficient versus time. This is when the creep coefficient would be starting after the 10th day of loading, and then there will be no significant creep coefficient or creep taking place after 10,000 number of days of loading. The number of steps, well, these are the steps which it is talking about. We can define many more number of steps according to the time and the value. Similarly, we have the graph for the shrinkage strain, and we can take the image of these graphs dynamically by clicking over here. That's all. So I'll just click on apply, and here we have the time dependent column property. As we see, it is in blue color because it has not been yet linked with the linear material property. Alright, so I'll go ahead now and define for the wall the same European code, same property, linear property was C30 and 37. Relative humidity I'll keep same, notional size of member. Now the program can calculate the notional size automatically for the frame elements, not for the walls. This is because the calculation of the wall notional size is very easy, because notional size is 2 into AC, sectional area, which is 2 into length into the thickness of the wall, divided by the perimeter in contact with the atmosphere, which is 2 into length. So that's why the numerator and denominator 2 into length go cancelled, and we can simply provide the notional size of member as thickness. So here I'll provide 0.3 because all my walls are having 300 mm thick wall thickness. The type of cement is N, type of code is general structure, and age of concrete is 3 days. I can still see the results in the form of graph and click on OK and close. So creep shrinkage is done. Next is the compressive strength. I'll click on add. Now this compressive strength is irrespective of the geometry, so I'll simply provide one compressive strength property using the European code and provide over here the mean compressive strength at the age of 28 days, which is FCK plus the delta F value, which is 1.15. Now all the bottom mass calculations are acceptable by MIDAS Gen, so no need to worry. All you need to do is go on, say, redraw graph and click on OK and close. Next is the change property. So auto calculate notional size of members. I'll select all the elements and click on apply, and we can go to the tables of this notional size and see how the program has successfully calculated the notional sizes of each and every frame element. Next, I'll go ahead with the material link and link the linear material properties with the time dependent material properties. So I'll select column and compressive strength and column linear material property from here and click on add. Similarly for the walls. Now the time dependent material properties have been successfully defined and assigned to our structure. Next thing, we will go ahead and apply the construction sequences to our model. So here we have construction stage and we can define construction stages by ourselves. Basically, this is the reason why it was possible for SKS Treno to have the top to bottom construction sequence. All we need to do is provide the duration, provide over here we need to create the groups for elements, boundaries and loads, and then activate them or deactivate them in the construction stage. However, in this session I'm going to be using a very special feature, that is construction stage wizard. So all I have to do is simply go to the construction stage wizard and here just click on automatic generation. Then we need to provide the information of the construction sequence, like the story increments, the stage duration and the member age. The story increment basically is how many number of stories are going to be constructed in one construction stage, then the stage duration and the member age. Now for understanding these all parameters, we will go back to the presentation. This is the construction schedule to be followed. There are 3 levels of shoring, hence the stage cycle reduces to 7 days. The time of removal of lowest level of shores from concreting of top floor is 5 days. With this information, we see here graphically the actual stages. On first day, formwork is installed. After 3 days, concrete casting is done. Here it means that the member age is 0. Then on the 8th day, that is after 5 days, the next level formwork is installed. Two days later, the concrete for second level is cast. The age for the second level member is now 0. Again, after 5 days, the third level shoring is done. 2 days later, the third level concrete is cast. Now again, after 5 days, the next level shoring is done. As the level of shoring is 3 levels, the information we saw, we see that the formwork for the first level is removed. That will be from the 3rd day to the 22nd day, making it 22nd day, that is making it 19 days as the age of the concrete of the first level members. And this is the age to be provided in MIDAS. That is from the time of casting to the time of removal of formwork. Now after 7 days, we see the next level of formwork is removed, thus completing one cycle in 7 days. This is a summary of the schedule. This is the stages that we will be creating in MIDAS Gen. Up to 12 floors, the construction schedule is the same. The different part is on this 92nd day. The superimposed dead load is entered for first to third floor. And the day term is 3 days. and it is entered for further floors. "32 days later, after entering the last superimposed dead load, then the live load is entered on the 112th day. So this is what we will be applying in MIDAS Gen. So let's go back to MIDAS Gen program. So first thing over here, we will be applying the sulfate. So DLS is for the sulfate load case. The story increment is 1. The stage duration, as explained earlier, would be the 7 days, 5 days for formwork removal and 2 days for concrete casting. Then the member age, as we saw, from 3rd day to 22nd day, that is 19 number of days, is the age of the concrete right from casting to the removal of formwork. Further, I can additionally apply the superimposed dead loads. I'll select the load case for that. And the story increment, as shown in the sequence, it was 3 number of stories. And we already know the starting day, that was 71st day. And the day increment after that was again 3 number of days. The live loads can also be applied to the structure in the construction sequence itself. This live load, now I will be selecting the load case, and the story increment now will be directly 12. We already have 12 number of stories, so after the 12 number of stories are completely constructed and the superimposed dead loads have been already applied, that will be provided by the starting day. So the starting day after the superimposed dead load was completely applied was 112. And the day increment does not matter over here, we'll just keep it as 1. So here, after the complete structure has been constructed, and this is starting day, that is after the superimposed dead loads have been applied to entire structure, and the day increment won't matter because we are at once applying the entire live load. So I'll just click on OK over here and click on OK again. The construction stages have been successfully created by the program, and we can see that over here in our workstream menu. We can also change the construction stages and check how the elements have been activated, the groups. These also have been automatically created by the program. So in the first construction stage, we can see the material properties, and over here this is the static loads. So we can see over here only the DLS load has right now been applied. And as we go ahead on changing the construction sequence or the construction stage, as we move up, we can see now that at CS11 the dead load floor finish, that is a superimposed dead load, has got activated. So this is the construction stages display. Now I'll go back to the base stage, wherein I can go ahead and further provide certain loading information to the program. For example, now the creep and shrinkage material properties will be insignificant after 10,000 number of days. So we are interested in a certain number of days which will help us provide the result of a significant shortening. So I'll go ahead with the define construction stage command right over here, and all these construction stage wizard created construction stages can be modified as well, but I'll go ahead and add a last construction stage that will have 3 years of a duration. So duration is 1063 number of days, and then we can simply click on OK. Nothing else is required to be activated or deactivated. And now we will check the results for the 3 years later. Okay, so we have defined our own construction stage. Now we'll go ahead with the analysis. So before we go ahead to the analysis, we can see over here the construction stage analysis control. Conduct the construction stage analysis for all the construction stages until the last stage, or we can have the construction stage analysis performed only for the stage selected. So if we say CS06, then construction stage analysis will be performed until the 6th construction stage only. This is required when we want to check the results only for the construction stages. And there are n number of floors, so it will take maybe if there are 100 number of stories, then it will take longer duration for conducting the construction stage analysis. So in that case, I can, if I want to see the result for the first, second construction stage, or maybe even the 10th or 50th construction stage, then it will be easier for me to specify over here the last construction stage as CS01 or CS05, like that. So next thing is the analysis option. We have got linear as well as non-linear analysis. We can select the non-linear analysis if in case we do have certain tension only members or compression only members and so on. Then further we can get perform this linear analysis for accumulative stage or independent stage, and we can choose to include or not to include the time dependent effect that we have defined. Next is the load cases to be distinguished from dead load for construction stage output. As an output, the program provides the result as dead load, which is a combination of dead load of self-weight floor finishes as well as live load, which we have defined in the construction sequence. So to get the live load results separate from the dead loads, we can just simply provide this information right over here. So all I did was select the load case and click on add. So there you go, the load case was here. Then further, the time dependent effect, we can choose if only creep or only shrinkage is to be used, but I selected over here creep and shrinkage. So after this, we can just go ahead and click on OK. We see over here the analysis control data includes the construction stage analysis, and then we can go ahead and perform the analysis. Okay, so as we can see over here, other stage was selected, so the analysis has been performed only for CS01. So I'll just change this back to last stage and perform the analysis again. Okay, so within 13.64 seconds, our model has been analyzed. Next, we will go ahead and check the results. So in the results, we can check the reactions for every construction stage. So here we have CS01, CS02, and we can even activate the reactions with the values. So we can display over here the reactions, and these reactions will go on increasing because of the additional loads coming from the upper stories. So you can see over here the loads increasing. Similarly, we can get the results for the displacement contour, for the beam moments diagrams or shear force diagrams. So this is 272.3, and we can see for the last construction stage after 3 years, the moment has still increased to 271.5. So this is the reason why for high-rise structures we really need to conduct construction stage analysis. and then further figure out if the compensation has to be provided with respect to the reinforcements or by changing the height of the vertical elements. So this is the result for beam diagrams. Now, after the column shortening analysis has been performed, we need to check the result for the column shortening. So MIDAS Gen has got column shortening graph for construction stage. It's a very useful tool. So I'll go back over here to, this is post CS. No matter which stage we are, we can just go on and add a new column. So all we have to do is provide the location of the column. So if this is a C1 column right over here at 0, 0 coordinate, I can select from here which results I would like to look. So as this is an RC structure, we are going to look at the results of subto casting. So I'll select creep, elastic, and shrinkage right over here, and even the total subto casting, which is the summation of elastic, creep, and shrinkage. So I'll check on that as well and click on OK. And further, I can go ahead now and check on these results to be displayed with respect to the 3-year term period, and then click on Apply. So this is the graph that has been received, or that can be extracted from construction stage analysis. This one is for the elastic, creep, and shrinkage, and this is for the total subto casting result. We can get this graph in the form of Excel sheet as well. So this is the graph that has come up in Excel sheet. These are the values in meters. We can modify this in mm and then again take the result out. So a maximum of 14.67 mm is the shortening taking place. And that is at the 12th floor. We can save this graph as an image, as a text file. So this is regarding the column shortening analysis in MIDAS Gen. Let us look at some useful features for construction stage analysis in MIDAS Gen. The building wizard, as we saw in the demonstration. The construction stage analysis for composite members. And the material stiffness changes for cracked section analysis. As you see over here, we can define the stiffness changes in groups, and those groups can be activated or deactivated in our construction stages. There is also spring supports for soil interaction, which can be activated or deactivated. We can apply them in a boundary group for activation and deactivation in the construction stages. Now, in case of post-tensioning of members, the tendon losses can also be extracted from MIDAS Gen by performing construction stage analysis, and the loss graph is automatically provided by the program. So these are a few of the useful features in case of construction stage analysis. Now I'd be going for the question answers part. So there are some questions here. One of the question is the analysis speed fast for high-rise buildings, and how does it take usually? For example, the application which you showed at the beginning of the session. Well, the program has high analysis speed, as it has 64-bit solver speed, and to top it off, GPU accelerators can also be used. It makes the analysis speed really fast. Another question over here is, what are the advantages if we use composite function, which you show in the presentation? Okay, for this I would like to go back to the previous slide. The advantage here is that in construction stages, according to the construction sequence, we can activate or deactivate the inner steel section, basically activate the inner steel section first, and then activate the concrete part. This does include the effect of creep and shrinkage. Also, we can apply the stiffness scale factors to the parts. The program provides partial stiffness properties as well as the composite stiffness properties. Okay, there are some more questions. However, due to time constraints, I would be ending the session here. The answers to the rest of the questions shall be sent by email. So may you have any further queries, please write to us at techsupport@midasit.com. Okay, thank you everyone for attending this webinar session. We'll be answering you to all your questions by email. Thank you very much again. Have a great day.